So, if you've ever fired up a tool like Wireshark to look at a TLS 1.3 connection, you might have scratched your head a little bit. The messages, they don't always seem to line up with what you'd expect from a modern protocol. Well, today we're going to pull back the curtain on one of the most brilliant and kind of sneaky parts of the TLS 1.3 handshake. It's disguise. By the time we're done here, you'll totally get the clever trick that keeps our modern web secure.
All right, let's start with a little analogy here. Picture TLS 1.3 as this futuristic, unpickable, high-tech lock. But here's the problem. It has to travel through the internet, which is basically a delivery system full of old, sometimes clunky equipment. And this old gear, it only recognizes classic, old-fashioned padlocks. So, to make sure it doesn't get thrown out, our futuristic lock gets put inside a box that looks exactly like an old one. This disguise, that's the absolute key to understanding everything that follows.
Okay, so our investigation starts with the very first clue. It's a message that honestly seems like it's from a totally different era. It just pops up in the middle of this brand new handshake, and it's called the ChangeCipherSpec. Now, back in the day, with older versions of TLS, this message was a huge deal. It was like someone flipping a big switch, where both sides would agree, okay, that's it. From this exact moment on, everything we say is encrypted. Super simple, super clear. But as you're about to see, in TLS 1.3, its job is completely different. And when we zoom in and look at the nitty-gritty details of this message, we find our first major clue. Check out that protocol field. The data inside literally says TLS 1.2. But hang on. We know we're setting up a shiny new TLS 1.3 connection, so why on earth is it mislabeling itself? This right here is the first hint of that disguise we talked about. It's packaged to look like the old padlock, even though we know there's a futuristic one inside. And here, my friends, is the central mystery. The engineers who designed TLS 1.3 made encryption way more efficient. It starts much earlier in the process. They actually made this whole ChangeCipherSpec message completely obsolete. It has zero technical function in the new protocol. So if it's not needed, why is it still being sent? And why is it lying about its version number? What is going on? To answer that, we need to look at the real final step of the handshake. This isn't some dusty relic from the past. This is the true confirmation that our secure channel is up and running. It's called the client finished message. Think of this finished message as a cryptographic receipt for the entire setup. The client takes all the messages that have been exchanged so far, mashes them all together, and creates a unique mathematical fingerprint, a hash. It sends that fingerprint over to the server. This proves that both sides saw the exact same conversation and that no one in the middle messed with anything. And here's the really important part. This message is itself encrypted. It's the very first piece of data sent over that brand new secure channel. So how is it encrypted? With this amazing piece of modern crypto called AEAD. You know, old school encryption was like just putting something in a locked box. That gives you secrecy or confidentiality. AEAD not only locks the box, but it also puts this special, unbreakable seal on it. That seal proves the message is authentic, it came from the right person, and nobody's tampered with it. This is the futuristic lock we were talking about, and it's protecting the most critical part of the whole setup. Okay, so we have a fake message from the past and a real, super secure message locking things down in the present. It's time to connect the dots and finally reveal the secret behind this whole elaborate act. Why does TLS 1.3 play dress up? The reason for this whole disguise is spelled out perfectly right here. It says, certain parts of the handshake are intentionally hard-coded with old values, like that TLS 1.2 version number we saw. And why? To stop older network equipment from getting confused and just chucking the packets in the trash. It's a trick, a clever trick, designed to fool what the spec calls intermediate stations. So what are these intermediate stations? Well, we usually call them middle boxes. This is all the stuff your data has to pass through to get to the server. Routers, firewalls, you name it. A lot of this equipment is old, and it's only programmed to understand older versions of TLS. If it saw a packet proudly announcing, "Hi, I'm the new TLS 1.3, it might just panic, not know what to do, and drop the connection right there. Your website wouldn't load. And this chart just lays it all out perfectly. On the surface, the disguise that the old network gear sees, it looks like a totally normal TLS 1.2 handshake. It sees the right version number, it sees that familiar ChangeCipherSpec message. Everything looks fine. But underneath, what's really happening is that the client and server are speaking the new, faster, more secure TLS 1.3. They've already agreed to just completely ignore these fake messages that are only there for show. And it's not just the ChangeCipherSpec message, by the way. Other fields that used to be important in older versions, things like session ID and compression options, they're also thrown into the handshake just for looks. They're filled with dummy values, but TLS 1.3 doesn't use them at all. They're basically ghosts in the machine, just there to keep the old hardware from freaking out.
So this is all a really cool piece of engineering. But why is understanding this disguise so important? Especially if you're, say, studying this for a class. Well, it all comes down to what happens when you try to actually analyze this stuff in the real world. This is exactly why a tool like Wireshark is so critical for network analysis. I mean, can you imagine capturing this traffic without knowing about the disguise? You'd be pulling your hair out. You'd see messages screaming that they're TLS 1.2, even though you know for a fact a TLS 1.3 connection was made. Thankfully, Wireshark is smart. It knows about the trick, and it looks past the illusion to show you the real TLS 1.3 handshake happening underneath it all. And that right there is the #1 takeaway from all of this. If you remember one thing, remember this. When you're analyzing network protocols, especially for a system as massive and messy as the internet, you have to be a bit of a detective. The raw data traveling on the wire might be telling a story specifically designed to fool old equipment. Your job is to know the protocol well enough to see the truth. You know, in the end, this whole clever disguise really highlights a fundamental challenge for the internet itself. How do we keep innovating and making things better when we have to work with the reality of an aging infrastructure? The solution for TLS 1.3 was absolutely brilliant. But let's be honest, it's a patch. It's a workaround. As we start building the next generation of protocols, figuring out this problem, how to build the future on a foundation that's sometimes stuck in the past, that's going to be the key.